What I want to give you today is a broad overview of this field that I helped create about 22 years ago. And as most things that happen in science, almost by accident, because I was moving in a completely different direction. Of course, by training, I'm a systems neuroscientist, and since the beginning of my career, I was interested in very abstract issues on how the central nervous system encodes information, particularly tactile and later motor information. And in fact, when I went to the US to work with John Chapin in Philadelphia in '89, my main reason to moving out of Brazil and going to the US was to be able to do what you're seeing this slide here. In the late 80s, it was pretty clear to some of us, not all of us, but some of us in the neuroscience community, that we could not keep going with the methodology, the electrophysiological approach that had become very classic, recording the extracellular activity of one neuron at a time. And as you know, our brain has 86 billion neurons. And I used to make a comparison that recording one neuron at a time, trying to understand how the human nervous system works, is like going to the Amazon forest and trying to understand the ecosystem of the rainforest by going one tree at a time. Not very good idea. It will take a long time to make sense of the data you collect. So I came to the US because John Chapin was the only guy at that time that shared the same view that I had, that we needed to look at populations of brain cells, populations of neurons simultaneously, to try to understand how the brain works. It doesn't matter if you're talking about a rodent, a cockroach, or a human brain. The brain is about populations. And this is the first time in my lab at Duke that we recorded 100 neurons, the extracellular signals of 100 neurons in a awake, fully behaving rhesus monkey. And this is just a few seconds of this storm, this electrical storm taking over the frontal parietal lobes of the brain of this animal as the animal is preparing to make a decision. And as it turned out, I'm going to show you in a moment, John and I look at this 22 years ago, and we basically found a way to look at these patterns in real time and predict about 100 milliseconds ahead of time what these animals were about to do. And that was when we created this field called brain-machine interfaces. But just to give an idea, it was a long journey. I did a postdoc 4 years with John, then I moved to Duke in '94, and I had been there, until I became an emeritus professor last month. And in parallel, I created this institute here in Brazil. And for, this almost 4 decades, I have been looking, for the most part, of how cortical circuits explain primate behavior, and basically trying to map the dynamics of these circuits and how much they can change themselves dynamically through a property that we call brain plasticity. So I did this for 20 years, and at that point, when I met John after a few years, we realized that we are the first ones to look at how these big circuits operate in real time, not in deeply anesthetized animals, but in fully behaving animals. And from the data we collected together, and then after I moved to Duke with my students over the years, we derive a few principles that today have been reproduced by many independent groups all over the world, called principles of neural ensemble physiology or neuropopulation physiology. And back in '98, I never forget that, because it was a dinner that John and I were having in Philadelphia, in the outskirts of Philadelphia, in the most famous cheesesteak joint in the city. If you don't know cheesesteaks, you don't know anything about Philadelphia. Cheesesteaks are 1 foot long, as they say, cheese and a little bit of meat sandwiches that you eat, and they're the most popular lunch you can get in Philadelphia. So we're having this meeting together, in this famous restaurant, surrounded by truck drivers. They were, stopping at I-95 to have a lunch in this famous place. And John and I were debating how could we convince our colleagues that it's not about one neuron, but it's about populations. And at that time, we were eating and talking about, and we said, well, maybe if we could link brains to machines and demonstrate that we can only control robots to do what animals and humans do with their motor cortices, controlling their own bodies, maybe if we link brains to machines, we can have demonstrations that will be completely unequivocal, and we can demonstrate our theory on how the brain operates. And the moment we said, let's call it brain-machine interface, this new area, a huge truck driver stood up behind me, came to us full of cheese in his bird and said, that's a great name. So we had an instantaneous peer approval of the new name of this field. And long and behold, this took over. And in 2 decades, it has become one of the hottest areas in neuroscience, particularly because it can take basic science discoveries like the ones I'm going to show you in a moment to the clinical arena. And it can now provide complete new therapies, non-pharmacological therapies. That's a very important point. You can now interact with the brain in a therapeutical way that doesn't require any drug to be administered to these patients. And I'm talking about things that when I went to medical school here in Sao Paulo, my neurology teacher told me never to work on because I would never find any therapy or any treatment. Things like spinal cord injury, Parkinson's disease, chronic epilepsy, untreatable chronic epilepsy. And long and behold, 20 years after we created this area, now we have things called neuroprosthetic devices that are being introduced to treat exactly these diseases that today account for hundreds of millions of people around the world. So it's almost like we are witnessing the dawn of a new type of neurology. And it's coming not from the pharmacological arena, but from new ways to understand how brain dynamics works and how it goes bad when the system is disrupted by whatever cause that generates a neurological psychiatric disorder. In fact, from these studies, I have come up to a complete new theory of the brain. I have just recently published a book on it, and basically proposed that a unifying theory on brain disorders, ending with this distinction between neurological and psychiatric disorders and unifying this. And I hope I can tell you a little bit about it.